All right, welcome back everyone. Next up, we have a section that I'm going to say is the least important for the entire course. That doesn't mean that I don't like it. I actually think it's very interesting, fascinating behind the scenes peek at how Git works, but you really don't have to understand any of this in order to use Git. So far, we haven't really talked about it, we haven't understood it, but we've been using Git just fine. So a lot of Git users won't go into any of this, or they won't be bothered to understand things like Git objects and blobs and trees and how Git hashes things. And, it's important to understand to make you a more well-rounded Git developer, I guess, but it's not critical to actually using it. Anyway, let's start by highlighting probably the one thing that I would say is slightly more important. At the beginning of this section, we're going to talk about the contents of the .git directory and just take a look at some of the more important pieces. So I'll show you the local config file. It will come up probably for you at some point if you continue using Git. And it has more real-world applications, I guess, than some of the more conceptual things. So everything else, understanding the refs directory, not that important. Understanding the head file, we've already seen it actually very early on when I first introduced branches. Then when I talk about hashing functions and Git objects, Git trees, Git blobs, all of that stuff, and I'll show you some commands, some new Git commands they're called plumbing commands. They're for behind the scenes usages. They're not really consumer facing commands, as much as you could say any command in Git is consumer facing. But anyway, that's all encompassed in these two at the bottom. So all of that is nice to have. It's great if you watch these videos, if you make it through them, if you find them interesting. But if you struggle to understand some of what I'm talking about, if I do a poor job of teaching you these concepts, you will still be a perfectly fine Git developer. But let's hope that I don't do a poor job. Okay. So the first part of this Git behind the scenes section will focus on the .git directory and its contents. There's a lot in there that we're not going to talk about, but I'm going to highlight some of the most important pieces in the next few videos. So if we take a look at any repository, I'm going to be using the React repository that we cloned in the Git tags section, but you can do this on any repo. But just to remind you, there's a whole bunch of stuff in this one. If I do a git log, well, that's not very helpful. Let's do a one line. Lots and lots of commits. I mean, a lot. Okay. And then we've got, of course, our .git folder. So I'm going to take a look at that folder. I'll just cd into it. Remember, it's a hidden folder. Let me clear. And then here are the contents. So compared to this slide, there's a lot more. But I'm just going to highlight some of the most important pieces. And in this video, I'm going to start by talking about this one file called config. The config file is for additional configuration. We've talked about this a little bit. With Git, there are multiple locations that we can configure settings. We can do it globally. We can actually do it system-wide, globally, and then locally on a per repo basis. So this config file in the .git folder right there, in every repo, it's going to exist. If you put settings in there, they will be configured for this one repo, but not for all repos. It's not going to change things globally. Now, there is also a global config file, which we won't talk about now. I just want to show you the local one. This is where we can go and change things. We can add customization for one repo that won't affect another repo. The problem is that there is so much that you can do, so many different settings, it's honestly overwhelming. Here is what the file looks like. So the format is a bit different than anything we've seen so far. This is what's in mine by default. So every time I add a remote, I cloned this repo. So we ended up with this remote first. And then I added my own remote. I called it Colts. So we end up with this here. But then we have some settings that we can change. Some of these basic ones like ignore case. They're in here automatically, but I can add on as much as I want. And this is also where we can add Git aliases that we'll talk about later. So I said there's a lot that you can do. This is the documentation, the page for Git config. We can configure Git, we can change settings from the command line, which we've seen before when we did this sort of thing. Git config user.name, for example. When we set this, if I set it to something else, I'm actually setting a value in a file, in the global Git config file. but I can also set things locally. So I could do git config and then local user.name. It's not going to give me anything, but I can set this value to be something else, like, I don't know, Chicken Little. Okay, and now if I ask for my local username, it says, you are Chicken Little. And if we look at this file, somewhere, there it is, user name is Chicken Little. So if I set email, local user.email, I don't know, how about chicken@gmail.com, we can see it is just a simple way of updating the file for me, right? I'm setting a local setting versus if I leave off the -- local, I'm updating a setting in the global config file. So in another repo, I'm still Colt. That's the global user.name. In this repo, I am now Chicken Little. Also, we can do a whole bunch more, which is what I was starting to get at. So many different settings. It's very, very overwhelming as I scroll through here. Each one of these is a setting. And most of them have multiple possible values. I mean, it's kind of crazy. So if you do want to get into fancy configuration files, I usually poke around and take a look at what other developers do. They often share their config files. I'll just show one example of things that we could configure. It's, I guess, kind of fun. We'll play around with color. So depending on the terminal you're using, the shell specifically, you may have some colors automatically configured. For example, if I do a git, I have to get out of the .git folder. If I do a git diff, let's just do compared to a couple commits ago. I've got this default red and green on this diff and some cyan here. You may or may not see the same colors, but I'm going to show you how we can actually change that. So there's all these settings under color. If I try and search for color, this is what I don't like. I'm searching for color and I'm getting 151 results. It's really hard to navigate this, but basically I happen to know how to do this because I've pulled up an earlier example, and I think there's an example somewhere on here as well. But I'm just going to show you what it's like. I wouldn't come to the Git docs to figure this out. I would probably Google just git config colors. So I'm going to show it to you over here. I can manually edit this file instead of going and using the commands from the terminal. I can do this. So I'm going to start with color. And again, the syntax kind of weird. I'm going to say UI equals true. All right. And then after that, I can set colors for different parts and different commands. So for example, for the output of git branch, this is the syntax: color space branch, and then indented. I can then change what the current branch looks like, what a remote branch looks like, what a local branch looks like. I can change their colors. So I'm not sure what we have right now. If I do git branch, okay. Well, I'm in detached head. Okay, let's go back to master. Git switch master. Okay, let's do git branch again. So my current branch is green right now. And if I make another branch, let's just call this new branch. Yeah, so it's green, and then the other branches that I have locally are black. So I can change that. I could say all local branches equal, and then I can come up with a color. There's only so many color choices. It does go into it on the docs somewhere here, but of course I can't find it. Here we are. Black, red, green, yellow, blue, magenta, cyan, and white. Let's do, let's do cyan just to show this. And then I can also set a weight, like bold. But I guess I'll do bold, sure. Okay, so if I save this and I run the command again, now you can see when I run git branch, the output for all branches except the current one I'm on, they show up as cyan and bolded. So I could also say that current, this is just another keyword, equals yellow bold. Now if I try it, that's my terminal's version of yellow. These are colors that you can actually configure, and yellow doesn't even have to be yellow. It's up to the terminal that it's being displayed in. Color is kind of a confusing topic with terminals. Anyway, there's other things we can do, right? Besides just bold, I think we can do, blink, reverse, italic, strike through, dim. So I don't know if we want to do any of those, but I'll just show if we leave off bold, like for local branches, it's not bolded, it's just sort of the default font weight. And then we can do other things, like if you want to set the colors for get diff or for get status, you can set all of those commands. So I'll do color for diff. It looks like this. And then indented, we have things that we can set, including old. So what the old stuff looks like, what color it is. New. So right now, if I just recall this command, you can see that new is already showing up as green. And is there any old? I don't see anything. Let me try a couple commits ago. Here we are. So you can see red and green, and then we've got this stuff that's in cyan. I don't know. I don't want to waste your time showing all this, but I'll just quickly say old is now going to be magenta in bold. Sure. And if I run get diff again, you'll see I have magenta showing up for the old, the minus signs. So just another example of configuring things. There are other things we can do. You can change the text editor locally for whatever reason. I wouldn't do this, but you could for this one repo. There are many, many settings, but a lot of the time you want them to go in your global git config. But I just wanted to show you that you can screw around. Well, I won't say screw around. You can have fun with this git config file. It's located in every .git folder. It's just called config. And I'm looking at it right here. Kind of weird syntax, terrifying docs, intimidating to try and understand, but there's just so many settings you can play around with. So you can set them from the terminal, as I showed you, with the -- local flag, or you can set them manually in the file. Okay, so that's the config file in the .git folder. So the next piece of the .git folder we'll cover is the refs folder. So in every Git repo that you make, there's going to be a refs folder, and inside of that refs folder, there are a couple of different subdirectories, and we'll start by talking about the heads directory. But actually before that, refs for references is where Git stores all of every time I've talked about a pointer or a reference, whether it's a branch pointer or a tag, two different ways or two things in Git that refer to commits, those are stored, they actually exist in the refs folder. So that's what refs is, references. So we'll start by taking a look at branches. In this refs/heads directory, Git makes one file for every branch in a repo. And that file will have the name of the branch. So when I've shown diagrams like this in the past, where I've shown or I've illustrated branch references with an arrow, like a label and an arrow, these references are just files in that folder, in the refs/heads folder. So if we had a branch called dark mode, there is a file called dark mode, and there's no arrow, but inside the file, there's a commit hash. It points to a particular commit. So in this repo, this is the React repo. Let's see, we've got 3 branches here. And if I just show you inside of this .git folder, I'll just show the contents, .git/, and then we've got refs right here. So I'll just print out the contents. We have heads, remotes, and tags. Now, you may not have all of these, depending on if you have any remotes, if you have any tags. Also, I forgot to mention that if you started with a brand new empty Git repo, things are slightly different than if you actually have a commit in there, if you have stuff being staged, if you have history. So everything I'm talking about is once you have at least one commit and at least one branch. Okay, so inside of this heads directory, I'll print that out just like this. You'll see we have 3 files, one for each branch. And each one of those files contains a commit hash. So why don't I start with a git log? Actually, let me just open up the contents here. Okay, so I have it in VS Code, my .git folder for this one repo. If I look at refs, heads, here's the 3 files. Let's take a look at new branch. I think that's a branch we're currently on. And it just has a commit hash in here. 796 is what it starts with. If I do git log one line, we can see this is where new branch is. This commit, 796. But we have some other branches, I think. Actually, maybe not. we've got these remote branch, but all the other branches here, master, new branch. Okay, well, why don't I make a new commit instead? As you can see, master and new branch refer to the same commit. This one doesn't. Branch from tag, I made that a while ago in a previous video. It refers to a different commit. Just like this slide, where we have one branch pointing or referencing one commit, and a different reference over here to a different commit. So if I make a commit on this new branch, do I have any changes here? Nah, of course not. Let's just make a file. Touch new file .js. Let's add new file. Let's commit it. Add new file. Okay, so now if I do a one line git log, this new branch is referencing this commit 5fb, and we see that here. It says 5fb. Master, though, has not changed. It's exactly what happened here on this slide, where if I go back a bit, at one point we had two branches pointing to the same commit, and then they diverged, right? In this dark mode reference file, it's now pointing to a new commit. And when I say pointing, it's just a commit hash stored in a file. So if I make one more branch, if I branch off from where I am now, git switch -c for create, what should we call this one? Just chicken. What do we see? We have a new file in that refs/heads folder called chicken, and inside of it, it has the tip commit, the tip of that branch, which chicken, we just created it from new branch. So it has the same commit hash right now. We're pointing to the same commit, 5fb, 5fb. All right, so inside of this directory, we also have a tags folder, and tags are just pointers as well. So you see some of the tags that I created. Each one has a commit hash, and then the name of that file is the name of that tag. So just another reference, hence the refs directory. And then this remotes folder, you can see for each of the remotes I have set up, there's a directory, and I'll just show you what we're looking at right now. If we pay attention to origin here, if I do a fetch, so this is a React repository, if I do a git fetch, just everything, it fetched from the origin by default, which is the React repo, not my fork, but the official React repo. If we take a look in here, now it's been updated because we have this new, remember we talked about remote tracking branches. It's keeping track of the commit that origin master, so the master branch on origin, this is where that tip of that branch is. I don't have that. That is not actually on my local working directory. I know about it, or my Git repository knows about it. It has that commit here, and this is how it's able to do things like when I type git status. If I go back to master, rather, and I type git status again, it tells me you have diverged. But long story short, this is the same concept, right? A reference to a branch, but instead of a local branch that we have, this is something that's updated when we fetched or when we pull. These are references to branches that are on a remote. So that might be the origin remote, the master branch, or the cult remote, the master branch, but there could be many, many other branches on there. I just don't have them currently. All right, so that's a quick exploration of the refs directory. It's just a place that stores all those references. Every time I've diagrammed something like this, where I have a branch pointer referencing a commit, it's just a file with the name of a branch, and in that file, there's just a single commit hash. And then there's a bunch of them, one for each branch, and they're stored in the heads directory, where it's also a tags directory and a remotes directory. Okay, next up, this will be a quick one. We'll talk about the head file. So head in all caps, that's the name of the file. It exists in our .git directory. So if we take a look at .git, there it is, head. And it's just a plain text file. And it contains a reference to a commit or to a branch reference normally. So as we've talked about in our diagrams, head typically refers to a branch pointer, but we can go into detached head, at which point head refers to a particular commit, and that's why it's detached. Detached, detached. Okay, so we can take a look at it. Currently, I'm on the master branch on this React repo. Here's the head file. And it says inside of it, so I'll make it a bit larger. It just says, okay, take a look at whatever is in refs/heads/master, which is a commit, as we saw in the prior video. So it's a reference to a reference, right? It is pointing, if I go back, here we are, it's pointing in that file to the contents of the master reference, master branch reference. If I switch branches, what do we have? Let's switch to chicken, git switch chicken. Now it contains refs/heads/chicken, and we can take a look at that. This is the commit it's referring to. It's not pointing to the commit though, it's pointing to the branch, and the branch is referring to this commit. That's the tip of the branch. However, I could go back, right? If I pick one commit, let's just pick one of them, doesn't matter, right here. If I copy this hash or just a portion of it, and I do a git checkout with that hash, we've seen it before. I'm now in detached head. If we look at the head file, now it directly points to the commit. So the branch reference has not moved. It's still pointing to that 5FB, but head has. Just like in this slide here, we detach the head, it refers to a commit. The branch reference is still in the same place, it's just pointing at that commit. It contains the commit inside of the file. Now head contains a commit instead of containing a reference to a branch. So now if I get out of this, let's go, this time let's go to master, git switch to master. Now head is updated to reflect that change. All right, so that's the head file. So next up, we're going to talk about the objects folder. Now this folder, we're going to spend quite a lot of time discussing over a couple of videos. This is really the core of Git. This is where all of the backups of our files, all the content is stored, all the commits live here. And the way that it works is a lot to explain, but it's also interesting, and I think hopefully if I succeed, this section will make sense. This is the important stuff I want to cover in this section. It all has to do with hashing, and we're going to talk about things like blobs and trees. Anyway, we'll get into that. But in this video, I just want to show you it exists. There is a folder, right? If we look in the .git directory, if I can spell it, of course, called objects. And if we look inside of it, it's right here. So let me close down head. Objects here has a bunch of subdirectories, at least on my repository. I'm using this React example. So if you have a repo and it has some history, you'll have something in here, but probably not the same combination, the same digits. But anyway, we have these 2-digit hexadecimal folder names, and then inside of them, there are files. But then it tells me, I can't display it for you. It's either binary or an unsupported text encoding type. So we're not going to be able to look at the contents. This is what it does when it tries to display in VS Code. These are compressed, encrypted binary files. So they're not really meant for us to look at all. They're meant to be small. But those files store all the Git history, all the commits, all of the files and their information, the contents of files. Git stores full snapshots. It does not store diffs or changes, like a delta between two commits. It stores full complete snapshots, which is somewhat unique. So we'll talk about that. But inside of this folder, there are really 4 different types of basic Git objects. And this is what we're going to spend a lot of time talking about in the next few videos. Those 4 types are commits, trees, blobs, and annotated tags. So these are 4 different things that are stored in this objects directory, really the core of Git. They're all going to be hashed. We've seen the commit hashes before, those long crazy strings. We're going to learn a lot more about those in the next couple of videos. So where does this come from? What does this mean? Not the contents, but what do these file names mean and these folder names? Those are mysteries that will hopefully be explained soon if I do my job. I just wanted to introduce that folder. So there it is, the objects directory. It contains all of the data in a repository. So in the next video, we're going to start by talking about hashing. So to fully understand how Git works, we need to take a small side trip away from Git to talk about hashing functions. If you're familiar with the topic, the concept of hashing, you could skip this or maybe just skim it. We'll get back to Git specifically in the next video. But of course, this is all connected. So let's get going. So you've probably come across, I don't know why I said probably, you have definitely come across these long strings of characters. They are hexadecimal characters, exactly 40 digits long. If you're not familiar with hexadecimal, it's base 16 instead of base 10 decimal for a numbering system. So base 16 means we run out of digits that we use, at least in the decimal system, 0 through 9. So then we move on to letters, A, B, C, D, E, and F. I forgot F. Okay, so we end up with these very long strings, which are numbers, and they're all exactly 40 characters long. We've seen them before. I've used the term commit hash or just hashes. So what exactly are those? Well, they're the output of something called a hashing function. So hashing functions are a family of functions that have one goal. They take inputs of arbitrary size, meaning inputs of a variable size, small, large, and then spit out outputs of a fixed size. So in this example, whatever this hashing function is, it spits out, I'm not sure how many characters this is, but whatever it is, you can see that both outputs are exactly the same length, same number of digits. It doesn't have to be hexadecimal. Any number can be turned from hexadecimal to decimal or to binary, right? Numbers are numbers. This is just one way of representing them. They would be a little bit longer if this was a decimal number. Anyway, it's a fixed size. So the input here is a sentence. The input here is 3 characters. The input could be a file potentially, or it could be a single number, and it spits out fixed size outputs. So you may have come across hashing functions in computer science contexts, talking about data structures like hash tables, or you may have come across the term cryptographic hash functions, which is a subset of hash functions. They do the same thing, right? They map data of some arbitrary size to an output of a fixed size, but they have a couple of additional constraints. And this group of hashing functions have a whole bunch of different applications in information security, digital signatures, cryptocurrencies, as well as Git. So I'll just run through some of these really quickly. Probably the most important one to talk about up front is that cryptographic hash functions need to be deterministic, meaning that the same input always yields the same output. In other words, if we go back to this example, I love chickens should always yield this output. Whatever it is, if that's the input, it should always yield that output. LOL should always yield this output. So whatever the output is, it should be consistent. There shouldn't be any variability in what you get for the same input. Another constraint is that a cryptographic hash function should be a one-way function, meaning that if you have the output, it shouldn't tell you anything about the input. And along those lines, you shouldn't be able to guess or infer anything about the input. You shouldn't be able to reverse engineer if you have the output. So if I were to implement a password login authentication for users on a website, we use a hashing function to store the hashed output of a password. Let's say these are 2 passwords. If somebody gets access to our database, a hacker, a bad actor, they see these password hashes. They shouldn't be able to infer anything about the actual passwords. So that's important in a lot of situations. Also, a small change in an input should yield a large change in the output. It goes along the same lines, right? I shouldn't be able to guess I love chickens yields this. I should not be able to guess what I love chicken will yield. They shouldn't be connected. And then also, it should be unlikely to find 2 outputs with the same value. We want to avoid collisions whenever possible. So mathematically, with these hashing functions, it is possible to have collisions, of course, but the probabilities are so low that we really don't need to worry about it. Anyway, those are the basic rules of cryptographic hash functions. Now we're talking about Git here. We're not talking about cryptography. We're not talking about authentication or cryptocurrencies, but Git uses one of these hashing functions called SHA-1. Although this actually is set to change eventually. It's something that the group behind Git has said we plan on changing. We don't know when, and it's going to be a nightmare to change, but we plan on it at some point. But at the end of the day, there will be some replacement that will be just another hashing function. And this one, SHA-1, has been around for a little while, and it's a hashing function that always generates 40-digit hexadecimal strings. So the output size is fixed, right? We've talked about that. And all of the hashes we've seen are the output of the SHA-1 algorithm. So there are a handful, more than a handful, but there's a set of known or commonly used cryptographic hashing functions, including the SHA family, but there are others. MD5, ECDSA, is that what it is? ECDSA? I can never remember. Yes, ECDSA. Anyway, there's a group of these algorithms that are most commonly used. I just want to end this video by demonstrating some of the principles of this SHA-1 algorithm or any cryptographic hashing function. There are many websites that let you play around with different hash functions. So I've selected SHA-1 here, and then I can put any input in here like H, lowercase. I'll hash it, and here's the output that we get, 40 characters of hexadecimal. But I could also do HE, or how about a capital H, just to show you. We get a very different output, 27D54. Now we have 7CF, completely different. There is no connection. Now, if I do something that's really, really long, like imagine a whole file of JavaScript or a couple thousand lines of CSS. I'm just going to duplicate this a bunch of times. We're still only going to get 40 characters out. Okay? So Git uses this algorithm, SHA-1. You can see some of the other hashing functions here, common cryptographic hashing functions. But for us, we only care about SHA-1. We don't need to know anything about how it works. We just need to know that it satisfies the requirements to be a cryptographic hash function. Even if it's not that commonly used these days outside of Git, it is used in Git. And let's talk about how in the next video. So that's coming up. Okay, so if you skipped the last video because you know hashing functions, the only thing you missed relevant to Git is that Git uses a specific hashing function called SHA-1. Although this is set to change eventually, it still uses SHA-1. It generates 40-digit hexadecimal numbers, exactly what we've been seeing. This is the output of the SHA-1 algorithm. This is as well. And these are commit hashes, right? 40-digit commit hashes. But Git actually uses SHA-1 in many, many other places, not just to generate commit hashes. If you recall, let me find the slide. I mentioned that there are 4 types of Git objects, 4 types that Git can store, including commits, but then there's also trees and blobs and annotated tags, all 4 of which are hashed using SHA-1. So we're going to get to all 4 of those data types or object types throughout the course of this section, but I want to start by just explaining something about Git. Git is a key value data store, meaning that we can put data into Git, right? We ask Git to store something for us. That could be a file, it could be a folder, or it could be 100 files and folders. We could even just tell Git to store a piece of text for us, which we really don't do because all the times we make text in a file. But I'm about to show you, we can just give Git a piece of text and have it store that as well. So we can put all sorts of content into a Git repo, and Git is going to hand us back a unique key that we can then later use to retrieve that content. Like when you go to if you ever go to a bar or a club or a concert venue and there's a coat check, right? They take your coat, they give you a unique key that corresponds to your coat, and then later on you go back and say, hey, here's my key, give me back my coat, please. So the keys that we get back in Git are SHA-1 checksums, or the output of the SHA-1 hashing function. So here's a demo. Imagine we have a file called app.js, and I'm using Git to track the changes, right? I've made one version of it and then a second version of it. And for each version, I've used Git to store that file and its contents. Now that's actually somewhat complicated to understand because it does store files and contents separately, but we'll get there. Anyway, each one actually gets its own unique key. So you can see the keys here. Okay, so they are the output of SHA-1, just like a commit hash, and they each correspond to some value, some piece of data. So if I have one of those keys and I tell Git, please give me the content for this key, it's able to use that and figure out, oh, I know what I stored under that. It's v2 of app.js. Here you go. So we've seen a basic version of this using commit hashes, right? Where we say things like, check out this commit hash. I want to view the contents of this commit, and we give Git that commit, and then it can go look up corresponding information. But what we haven't seen is that Git uses these hashes all over the place. It's fundamental to how Git works, but so much of it is hidden behind the scenes. So in the next few videos, we're going to walk through this. We're going to see these different data types and the role that the SHA-1 hashing function plays, not just to make commit hashes, but also for trees and blobs, and then also annotated tags, but they're kind of an afterthought for us. So let me summarize that, hopefully quickly. Git allows us to store any sort of data in it, and it will hand us back a key for that data. And that key will be a SHA-1 hash that we can then use at a later date to retrieve the information we stored. So a key value data store. We store stuff in there, and it gives us a key. We can then come back and give it the key to get that value. So we'll see that in the next video. All right, so in this video, we're going to take a peek at some of the internals of Git. Specifically, I'm going to show you a command called git hash object that I never really use except when I'm teaching, but I do think it explains a lot about how Git works. Now remember what we said in the last video, Git is a key value data store. We can give it any sort of information, including just a simple letter or a sentence, let alone files like we normally do, and it will give us back a unique key. So this command git hash object is one way of doing that. We give it some data, and then it will give us back a unique key, a corresponding SHA-1 hash based upon that data. Remember how a hashing function works. We don't really care about the internals and how it works, but we care about the fact that you give it some input, it doesn't matter the size, it gives us an output that is always 40 hexadecimal digits. So this example here, git hash object, and then a file, is going to take the content from a file, and then it returns a unique SHA-1 hash that would be used to store our object, but it does not actually store anything in this form. So this won't store anything for us, but there's a variant I'll show you where we can tell Git, actually store this information, and it will create a new entry in the objects directory. Remember, we talked about it. The objects directory is where all the information eventually is stored. All of our files and their contents and all this stuff we're about to talk about. So git hash object on its own is not going to be that useful just like this, but the next thing I want to show you is a somewhat complicated looking variant. This allows us to hash something that is not a file. This right here, echo hello. If you're not familiar with the echo command, if I just echo anything, it's just returned right back to me, echo, 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 and so on, except only one time. So we can take that output, which is just hello in this case, and then we can pipe it over to git hash object. And we pass in the -- standard in. That's one of the options that we can pass to tell git hash object that we want it to hash from the standard in, meaning hash this hello. It's a very complicated way of telling it, we don't have a file for you to hash, just hash this right here. So let me demonstrate this, all right? So I'll echo something. We can do hi, and then pipe, and then git hash object, and then -- standard in. And notice it's giving me back a SHA-1 hash, a checksum. It's 40 characters hexadecimal, and every time that I call it with that same line, every time I hash hi, I should always get the same output. Remember, it's deterministic. The same input should always yield the same output. So I could try this with something else. What would be another example? How about hello? We get a different output, same length, 40 characters, hexadecimal, but very, very different. So at this point, I actually haven't even initialized a Git repo. So the command that I'm showing you there is like a Git utility in the same way that I can run git init anywhere. My machine just knows git init. I can run git hash object anywhere. But now I'm in a new folder and I'm going to run git init. It's not a repo. And then over in VS Code, I've opened the .git directory. So I'm showing you the contents here, right? If I do ls.git, it now exists. This is the initial state of .git. Objects, it has these two folders, info and pack, but they don't have anything in them, and they don't really matter to us right now. So objects does not have any of our content in it. It's just the blank object slate. All right, so now if I try running one of these commands again, like echo hello, pipe, git hash object from the standard in, right, we see that output. I just want to make it very clear, objects is not changing at all. We're not storing anything in Git. This is just saying, hello Git. If you were to store this object or this information, just hello, if you were to store it, what key would it be stored under? And that's the output, but it doesn't store it. However, if we add on this additional option, -w, I think it's just -write, W for write, this is going to tell Git, to actually store our object. Actually take this information, in our case, the string hello, take that word, hash it with SHA-1, and then store that. So after we run this command, whether we do hello or some other string, I'm going to do hello because it's simple. And I kind of recommend that you follow along if you want to with the same exact string, so hello as well, because it will make a more consistent experience for you, because this is going to come back. All right, so if I just add in the -w, just want to verify, prove, nothing in there. Now, we got this hash as our output. Let's hit enter. We get the same output, but now if we go to objects, it might take a moment. Well, for whatever reason, VS Code is not wanting to refresh and show me. Let me try refreshing here. Okay, there we are. Whew. Okay, so it is indeed here. There's a new folder, CE. Well, that's a coincidence. Let me show you that output again. Of course, I wiped the screen. But if we run this command, that hash that we got starts with CE. CE and then 013. So what do we have? CE, and then what do you know? 0136 and so on. So there's this entry in the objects folder, and there's a folder inside CE, just 2 characters, and then the rest, the 38 remaining digits, are used to name this file. So this file is the most basic way that Git stores content. This file actually contains our content, and in this case it was just hello, but it's been compressed and encrypted, so we can't read it, right? It's stored as binary in there, but it is in there. We have successfully stored our first piece of data in our Git database. The very, very manual way. We almost never would do this. I can't imagine really doing this outside of teaching, but I hope that this explains a tiny bit. We're not done. There's a lot of pieces of the puzzle here, but I hope you understand that this Git hash object with this annoying syntax is taking our input hello, which always returns the exact same output from SHA-1, this output. But we told it to write with -w previously, and Git took that and it created a file for us. It's not exactly the same name, right? It's 38 of 40 digits that are the same, and then the first 2 digits were used to create the folder. That's just what Git does. So the objects directory, if we had 2 hashes that happen to start with CE, they would share this folder. But then if we have another hash that starts with something else, which I'm about to do here, what should we do? Let's do goodbye as well. So echo goodbye, and then pipe that, basically send the output to hash object and tell it to expect standard in. So I'm not writing this yet, but we get DD7E. So when I add this W, I'm telling Git, all right, store this, store goodbye. So it does this all the time, but not with strings, with files. But I'm telling it, store goodbye. So we're going to end up with a folder called DD, and then a file, 7E1 blah, 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 all the way to A6. And inside will be a binary, compressed, encrypted version of goodbye that we won't be able to read, at least not with human eyes. All right, so I'm going to add that -w and hit enter. And of course, we get the same output because it was the same input. It's deterministic. We should always get that same hash, assuming we give it the same exact input. So not an extra space, not an extra, uppercase, lowercase, hidden character, exactly the same. So I'm going to have to refresh here. There we are. Now we have DD and then 7E1. Okay, so I have 2 strings, 2 pieces of text that I have successfully put into Git. In the next video, I'll show you how to get them out using another Git command that is pretty rarely used. So now that we've seen how to store data in a very low-level way in Git, normally we use a whole bunch of other commands and Git hashes things for us, but we can manually tell it, hash this, turn it into a Git object and store it. So we've done that a couple of times, and we got these keys back, right? We have this one and this one. So imagine that I don't know what was stored in there, or it was a really long file that I stored. I want to retrieve that data out. I have the key, and Git is storing the information in these files. I just can't read them. So to get it out, there's a function, or there's a Git command called cat file, git cat file, and then we pass in an object hash. So that could be a commit hash, or it could be one of these hashes. This is not from a commit. It's from something called a blob. We'll go into more detail. But any of these hashes we get in Git, they all are tied to a Git object, one of 4 types. And we can get information, we can read them out using git cat file. Now this -p option tells Git to pretty print the contents of the object based on the type of object it is. So I could pretty print a commit. If I had a commit using -p, it would detect it's a commit and print it out as a commit. But we're going to try it with what we have. These are not commits. So I can copy the whole hash and do a git cat file -p. And then I'll pass in the whole thing just to start. And what do you know? It says, hey, I have something stored for that. I have hello. I can also give it way fewer, right? I could just give it a couple of digits and it can figure it out. Let's do our second value that we stored, which was goodbye. We got back DD7E1. Let's just do that. So instead of the whole hash, just that little bit, and it knows what it stored. We gave it the key. It gave us back goodbye. All right. So now what I want to show you is a little bit different. I want to use files. I want to have actually just 2 versions of the same file, both of which we'll be able to store manually using the command git hash object, and then we'll be able to get those versions back out. So let's make our new file. I'll just touch dogs.txt, and then I'm going to open it up in my editor. All right, here it is. And I'll put in some of my dogs, Rusty and Wyatt. Rest in peace, Rusty and Wyatt. All right, so I have one version of this file. If I look at that file, that's what we have in that file. So I can tell Git to hash it. I can do the same thing, git hash object. I don't have to bother with the echo and the standard in because I'm going to provide it a file. I want it to tell me what is the hypothetical hash I would get back if you stored this. I'm not storing it because I didn't do -w. That's what we get back. So assuming that file doesn't change, remember how this works. The same input gives you the same output. Well, that's really important for how Git works because it can very quickly tell, oh, this file hasn't changed. It's giving me the same hash that it had before. But as soon as I change anything, a single space, a capital letter to a lowercase, the entire hash changes and Git can detect that. Anyway, I'm going to store it now. So I'm going to add the -w. All right. So git hash -object dogs.txt -w. And if you're following along here, you can type this exactly as you see it, or just make note of the fact that your hash is different, and just use that hash when we come back to it. So just be consistent, right? If you do follow along with me, make sure you're getting this hash. If you don't, it's not a big deal. Just use that hash that you're getting instead of the one that I have. All right, so I'm going to do -w. I'm saying store this version of that file, dogs.txt, and I'll have to refresh VS Code, but there it is, 39E27, whatever. And that's what it starts with, right? 39E27, blah, blah, blah. So now if I do a different version, if I change what's in this file, Rusty Wyatt, pretend, I'm using Git. We haven't made any commits, to be clear, right? If I type git log, no commits. But if I add another dog on here, Rusty Wyatt, I had a childhood dog named Cheyenne. And how about Sirius Black? Another great dog. Okay, so a new version of this file. If I try hashing that, I won't store it just yet, but if I hash it, we get a very different hash now because things have changed. Small change, any change, should lead to a large change in the output. So still 40 characters, that hash that we get back from SHA-1 from Git, but it's very different. So let's store that one too. All right, so I'm going to do git hash object dogs.txt -w for write. So we should see a new folder called fd and a file called this, 915 and so on. So whatever you did, if you had changes, you should get a different hash. And in that .git/objects folder, there now is an fd, at least in my example, 915. So I can't read it, but we can use the cat command, right? Git cat file, which if I scroll up, where did it go? We used it recently. Maybe not. Anyways, there it is, cat file. And then I can provide that hash. So either one of these hashes. If I do this, let's take this one. get cat-file, and I provide that hash, well, it yells at me because I forgot to provide the -p option for pretty print. There we are. So we see the first version. Actually, this is the second version rather. But if I take the other one, and this is where it gets kind of annoying to watch me do this, but remember I have two versions. This was the second one. This was the first one. I'll just copy part of that hash. And then I'll do the same thing. Get cat-file-p. I forgot that. This was the other version. So Git is storing both of these. I can delete the file entirely. I could get rid of this file, dogs.txt, but as long as I don't delete .git, it still has both of these versions in there, and I can get them out without even making a commit. I told Git to store those things for me manually. So let's say I delete everything from, let's just delete the contents. I won't delete the entire file. Okay. If I wanted to restore the contents, I'll take the hash that we got back, this one that starts with FD9, just like that. Whatever you got back, copy it. And then let me clear this. I'm going to do a git and then cat-file-p, pass in that hash. But this time, I'm going to add it into that file. Was it dogs.txt? And take a look. It's been restored for me. And if I use the other hash, which I can't remember, but I could even just look in here. I think it was 39E275. We'll see if I'm right or not. Let's see, 39E275. There it is, Rusty and Wyatt. So what I'm doing here is telling Git, please go and take this key, find the corresponding value that was stored under that key, and then take the contents of that file. Right, each one of these files, it's binary, it's compressed, it's encrypted. Take that, turn it back into something that makes sense, and then stick it in dogs.txt. So I could still delete that file, I could empty it out, I could have some radical changes in here, which, I mean, we do this all the time with Git, right? And then we realize, oh shoot, I want to go back to an older version of this file. Well, Git stores them all in here, not because we're running this command or because we're running git hash object, but it's the same principle. Git is able to hold on to those files, it's storing them in that objects directory, and then at any point, we can say, okay, please go give us that. Let me redirect that into dogs.txt. And we're back to normal. Okay, so we're one step closer to understanding things. We have not made a single commit. Just want to be very clear. We have only hashed things, hashed files and hashed strings of text, and stored those, and we've been able to retrieve them using the hashes we get back. But that's not a commit. In fact, there's something called a blob, and in the next video, we'll expand more on blobs. All right, so in the last few videos, we've seen that we can manually tell Git to store characters, single strings like hello and goodbye, and it will store them in the objects directory. It creates a file using the hash. So here I'm just showing, the hash file. I'm not showing the subdirectory it's nested inside of. Technically, the hash, the first two characters make the directory name, right? And then the other 38 make up the file name. But anyway, it stores the contents, in this case, hello, in the file, and it names it with this key, with the hash. And then I can put something else in there like goodbye and chicken, or I could have different versions of files. Which is more realistic. I can have 100 lines in a file versus 1,000 lines in the same file, or store 10 different files. Git is going to create objects for each of them. And then at any point, we can manually say, hey, here's the key for something. Please go give me the corresponding data. And we saw Git was able to do that. So at this point, everything that we have stored, all of the stuff in this objects directory, they are examples of one type of a Git object called blobs. Binary large objects, blob. So this is one type of an object Git can store. Remember, there are 4. Commits are one. Blobs are another, something called trees we'll see next. And then annotated tags, we don't care about those so much. But really, blobs, commits, and trees are the most important. So a blob is used to store the content of a file. It is just the content of a file, just the insides. It doesn't include even the file name. It's just the content. So what we've done so far is created a couple of blobs. This is a blob, this is a blob, this is a blob, this is a blob. They are just content that we've stored. Now, what's interesting, as I said, is that the file name is not included. So you can visualize a blob like this. This is the content in a file, some JavaScript file. Git, of course, keeps track of a file name, and that's where trees come in. But Git stores the contents of a file separate from the name. And then each blob gets its own hash. We've already seen that. These are blobs. We created a blob. It got this hash. This is a blob. It has this hash, 39E275. This is a blob, CE0136. Blobs are a building block of the way that we use Git, where we have different files and different contents and different versions and commits. They play a very important role, as you'll see. But on their own, a blob is just a Git object that stores the contents of a file. Doesn't even include the file name, but it does get its own hash. So it's not a commit hash, it's a blob hash. They might look like a commit hash, but that's just because they're all 40-character hexadecimals, right? It's impossible to tell them apart, and they're the output of the same SHA-1 function. Anyway, that's an intro to blobs. In the next video, we get to talk about trees. Okay, so in the previous video, we talked about blobs, and it's kind of probably confusing at this point. We said blobs store the contents of files, but not even the file name, just the contents of files. Now, that's fine, I guess, if we want to do things like we have been doing, where we're storing a couple of words or the content of a single file and then spitting it back out, asking Git to return it back to us. But in a large project with hundreds of files and nested folders and a crazy structure, if I can just tell Git, check out this commit or switch to this branch, and it can change all of those files, all of those folders, it might delete some in my working directory. It might add a whole bunch of stuff. How is it able to keep track of that structure? It's not just the insides of the files, it's the relationships between the files. It's the structure of the directories. So that's the role of tree objects. Trees are Git objects that are used to store the contents of a directory. So blobs store the contents of a file, and trees store the contents of a directory. So trees actually contain pointers that can refer both to blobs and to other trees. So think about it this way. If we have one folder, and inside that one folder there is one file, well, Git would represent that with one tree, and that tree would point to or refer to one blob for that file. So each entry in a tree, you can visualize it like this, contains the type. Is it a blob or a tree? The two things that a tree can refer to or can reference. And then for each entry, we've got the hash. So this is not the commit hash. This is a blob hash in this case, right? We saw a blob like this one, 1F7. It's the contents of some file. Well, here's a tree, and it references that contents, that blob, 1F7, and it gives it a name, app.js. And then down here, it references another blob. Here's the hash. So it's not storing the contents in the tree. That's what the blob is for. This is the structure. This is the content. So we end up with references to blobs, but also references to trees because we have nested directories often. So in this case, in this tree, we're representing app.js and readme, two files, two blobs, but then there's an images directory and a styles directory. And each one of those would be represented with its own tree. And there will be blobs most likely in there, and then maybe more trees. So hopefully this diagram helps explain it a little bit. If this is my folder structure, two files, index.html, main.js, and then a directory, nested, called styles. App.css is inside and nav.css is inside. Well, Git would have a single tree to represent this entire directory. So we've got a tree, and then it has a blob that it refers to, and it names it index.html. So that's the contents of that file. Remember, the blob itself does not store the name. The tree stores the name, and then it references the hash of that blob. So this is that connection between a file name and the contents. 1F7, that's this blob. Okay, so then the same thing for this main.js file. It points to that blob, whatever that hash is, and names it. But then it refers to another tree called styles. And that tree contains two blobs, app.css refers to one blob, nav.css refers to another blob. So here's a more fleshed out diagram, complete with the actual hashes that match. So you can see we have a tree. This tree has its own hash. Every tree has its own hash. It's a get object. So this is stored in the objects directory. And we see there's a blob, 1F7A7 right here. So that is hashed and stored, and it's called index.html. Here's the blob. This is the tree that refers to it. Here's another blob, BE321, that matches this, and it's called main.js. It's a blob. So whatever is in that file is the contents of a file called main.js. And then we've got a tree, styles, so that's a directory, 98287, that's the name of that hash. It's not the name, but that's the hash we see here. And that tree stores two blobs, 10ABB, which is app.css, and then FFE77, which is nav.css. Those are the contents there. So the last thing I'll show you in this video, we're not going to make any trees right now, but I'm going to show you that in an existing repo that has history, we can view trees, just like we could use cat file to view blobs. We can use cat file to view trees. And we don't have a tree to reference in our own repository that we've been working on, but this is the React repository or any repo we've worked on. If we have some commits that we've made and we've added some files and folders and stuff, we will have a tree, at least one. As we'll soon see, every commit reference is a tree. Anyway, this command, get catfile-p, we've already seen, but this syntax, master, and then this caret tree, that syntax is a particular way to refer to the tree object that is pointed to by the tip of our master branch. So the last commit on master, every commit refers to a tree. This just gives us the most recent tree. So let me show you that. This is that React repo that has all sorts of commits, lots of files in here. You can see them, a couple directories, okay? Really just fixtures, packages, and scripts, and then files. Now, if I do get catfile-p, and then I'm going to do that weird syntax. So master and then caret above the 6, tree, like that. And I hit enter. It prints out, it pretty prints a lot of stuff. We could ignore this over here. This is the file mode, doesn't matter. But it also shows us if it's a tree or a blob, and then the hash for each, and then the name. So we can see for each file, we've got let's see, circle CI, that's a file. Somewhere over here, it's a hidden file, so it's not showing up there. Let's keep going down. Here we are. Authors, that's a blob, right? So the contents are stored with this hash. And I could actually view the contents if I wanted to. Let's take a look. How about, sure, the README. I could copy this, I'll keep it on my clipboard. But then I'll also show you there's trees, right? Here's a tree object for the fixtures directory. Here's another one for packages and another for scripts. There we are, the 3 directories. So I'll just show this here. If I take this hash that I copied, this was a blob hash. Remember, I can do catfile-p, if I can type, here we are, pass in that hash, and it's showing me the contents of the README. This is all the stuff from that README file. So quite a bit of stuff that it's storing there. It's not too much. The last thing I want to show you is that another option for this catfile command is to actually tell us the type of something. What type of get object? If I do -t, it tells me it's a blob. But if I instead do this, get cat-file, well, actually, why don't I just show you? If we look at the tree again, if I pick one of these trees, like this tree object that represents the fixtures directory, if I do the same thing, get catfile-t, with that, it tells me it's a tree. So there are 2 types we've covered so far, blobs and trees. We haven't seen how to make a tree in the same way that we saw how to make a blob manually. I showed you an existing repository, this React repo, but all that you need to know for now is that trees represent folders, the structure of a directory. And inside of a folder, we can have files, but we can also have other folders. So the tree itself contains, it's not an actual table like you see here, but inside of it, it stores a bunch of entries, references to blobs and to other trees. Each one has a name, And each one has a hash, a blob hash or a tree hash. And each tree, as we've seen, has a hash. And that's all I'll say for now about it. I know it's getting kind of complicated, but this is hopefully all going to come together soon. So now we finally get to talk about commits, our good friend. We've been working with commits for quite a long time. We've seen these commit hashes, but now let's talk about the actual underlying structure of the Git object, the commit. So when we make a commit, Git generates a new commit Git object, and it stores that just like it stores all of the other objects, the blobs and trees we've seen. It hashes them, it makes a file over here in the objects directory. First 2 digits make a folder. Inside of that, 38 digits of the hash that are remaining are the name of that encrypted binary compressed file. Okay, so commits are going to be stored in there as well. What we haven't really talked about is what a commit actually contains. We know that it contains a message because we provide that message. We've seen that it includes the author. But what we have not really talked about is the fact that commits also include a reference to a parent commit. We've mentioned that, but we haven't gone into a ton of detail. So that's a reference to the hash of the commit that came before. So really all we need to get the entire chain, the entire history of a Git repo is just a commit that links back to a parent. And then we can go look at that parent. It links back to another parent, and that links back to another parent. Anyway, commits have a reference to the parent commit, but also they have a reference to a tree object. So this tree object is just like the tree objects that we've seen, like this, where a tree can reference other trees and also blobs. So you can visualize it this way instead. Every commit has a hash, right? All the contents are hashed. To generate this, there is the parent at the beginning of this repo. There's no history, so the parent just doesn't exist on this one commit. There's an author, committer, there's a message, but the tree is the most important part that I want to talk about. When we run git commit, Git creates this new commit object for us, and it sets the parent to be the current head commit, so that makes sense probably, right? If we make a new commit, it's going to have the parent of our current head. So it would go over here and point back to this one. But also the tree that it stores in this commit. The tree is the current content of the index, the staging area. So there's an actual index file. But basically, everything that we have worked on, all our changes, everything we have staged and prepared to commit, when we actually run git commit, a tree is generated. So that tree will reflect the contents of the index, and then that is included in the commit. Then we have the parent that references the parent commits. So that's giving us the history, right? So this is giving us the actual contents of the directory, our changes, and that tree is going to include, most likely, other trees and blobs. And then there's the metadata, author, committer, message, and then that whole thing is hashed, and we end up with this commit hash. So if I make a new commit, remember what I said here, that when we make a new commit, the head commit is going to be the parent of that new commit. So this was head right here, now head is here, and it points back, this commit refers back to the commit before it, the parent. So every commit is tied to a tree, and that tree is something that represents the structure of the application, and in turn the blobs that it contains, all the data in the files. So we could go look at any commit, and we can see that tree, for that commit. We can take a look, we can inspect it. And then of course, if we check out a commit, if we make a new branch based upon a commit, Git is going to take that tree and use it as the basis for our working directory. So let me demonstrate that. Let me just show you an example here, just another diagram. So here's this structure we've talked about, trees referring to blobs and to trees, but a commit includes one tree. So this would be the state of our application at this time of the commit. And then we have the commit message and so on. So every commit has a tree like that. So here's a much more expanded diagram that just shows the details, right? If you look at the hashes all match. So this commit, its tree, its snapshot, C387, that's this one right here. And then the tree has blobs and trees and so on. So let me try to demonstrate this. Let's make a simple repo. We'll just start from, well, we've got this dog repo already, right? This one I have open. I haven't made any commits. So if you want to follow along, right, if you have a new repo, you haven't made any commits, that will work for us. So right now there are no commit objects. I have added manually, I've added some blobs, but you don't need those for this demonstration. What we do need to do is make an initial commit. So I have this one file, dogs.txt. Why don't I just commit that? So I'll do something like git add dogs.txt, git commit, add dogs file, or initial commit or something. Okay, so I just made a commit. And if we look at that commit with git log, we see the commit hash, we see the author, we see the date, and the message. But there is more to this commit. If I copy this hash, we can use the same command we've seen, cat file, git cat file, and then let's do -t for type. And we see that we have a commit object. Also, 79dd6, let's remember that. Over here, what do we have? 79, whoops, there it is, in the objects directory of .git dd6. This is where my commit is stored. But I can actually view much more about it. I can pretty print it using git cat file -p, which we've also seen. We printed trees, we printed objects, or rather blobs. They're all objects. This is a commit. And now what we see is a little bit different. When we pretty print this commit hash, we actually end up seeing the tree. So remember, every commit contains a reference to a tree. And this tree represents the structure of our application, the snapshot of our directory, the app, at this point in time when we made the commit. So we could copy this, and you'll see different hashes, almost guaranteed. But if you are following along, we can verify that is indeed a tree, right? If we do git cat file -t for type, it's a tree. But I can also do git cat file -p. And we see, okay, here's the output, or here's the contents, rather, of the tree. Just one file, dogs.txt. But now, let's make a second commit, and let's do some other changes. Why don't we make another file in here? So what do we have? Dogs. Let's just do, cats. I'll just do it from the command line. So I'm going to do echo meow, meow, and I'll redirect that into a cats.txt file. You could also just make that file yourself. I don't have the directory open here. I have just .git. But anyway, I have a file. If we look at it, it says meow meow. All right, so now if I do a git status, I'll add that, cats.txt, and then I'll commit. Let's just go with add cats file. Okay, so now we have two commits, right? Our first one, but this new second one. If I copy this hash, first of all, 5119, we'll see that over here somewhere. I may need to refresh this. Where are you? Here it is, 5119. All right, so this is that commit object stored here. Okay, so if we use cat file, git cat -file, we do -t, we see this is indeed a commit. But if I do the same thing with -p, now we see it has a parent commit. And this parent commit is the only other commit we have. Hopefully you remember it was 79dd. That is correct. It's referencing the commit that we made first. There's only two. So this was the first one. And it has a reference to a tree. And this is a different tree. If I inspect this tree, git cat -file -p, and then I don't need the whole thing, but just a part of this hash for the tree. Now we see it has two blobs. Okay? So the first tree from the first commit, that snapshot had one blob for one dogs file. That's all we had. This one, this tree, has two blobs. But what's important to note, we didn't change this dogs file. So Git doesn't give us a new blob. It keeps the same object. It has the same hash, meaning it didn't change. I can prove this. So we have fd91. If I go look at this other commit, so the parent commit, this is going to be, I'm scared to do this because it's just so many commit hashes and so many crazy looking SHA hashes. But if I look at this earlier commit, the first one, git cat file -p, and then we look at that tree, git cat file -p with a tree, what do we see? One blob. This was the first snapshot I made. We only had the dogs file, fd91. So here, my second commit, we looked at the tree, the snapshot, and there was one blob for cats, that's new, but the second blob is for dogs, and it still is fd915 because it never changed. But now if I change that file, right? I do something different in the dogs file, like I change it to be Sirius Black, character from Harry Potter. So that's the new contents of the dogs file. Well, now if I add that change, git add dogs, git commit -m, update dogs file. If I commit, well, I just did commit, and I look at that new commit, this one here, for EC and so on. If I take a look with git cat -file -p, all right, it's referencing the parent commit. That was the second commit, 5119. I just remember those numbers. And this tree now, 0E37, blah, blah. If we inspect that, cat file -p, it's still two blobs, one for dogs and one for cats. But notice here, 04998, that is a new hash for the dogs blob. Versus, if we go back up to the earlier one, it used to be, so many, here we are, FD915. So Git's not going to come up with new hashes and change these objects if it doesn't need to. If nothing changed in those files, the contents are the same. A blob stores the contents of a file. So right now, Git is storing this version of the file in one blob, and then it's storing this version of the file in another blob. And then the trees will reference one of those versions depending on what was in that snapshot when I made the commit. So I'm hoping maybe some of this is starting to make sense. If not, the good news is you could still use Git and not have to worry about this. But this is about as far as I want to go in exploring all of this. There are other things we can do. We can actually make commits and generate trees in the same way that we created blobs from scratch. But I think this is a good place to stop. Okay, so every commit includes a reference to a parent. Unless it's the first commit, there is no parent. And then a tree. So that's another type of Git object we've seen. The tree will contain a bunch of references potentially to other trees, if it's a subdirectory, or to blobs. And a blob contains file contents. So a tree is the place where we store, or Git stores the file name corresponding to a blob. And then everything's hashed. Blobs get hashed, trees get hashed, commits get hashed, and Git uses those hashes to easily determine if something has changed, because you change a single character in a file, that blob's hash is different. You change something in a directory, that tree's hash is different. But also, it uses those hashes as keys so that it can easily retrieve things, right? Keys are supposed to be unique in a key value data store. So if I say, Git, give me the information from this commit, FA4, it can easily go and find that. Or give me the information for this blob. We usually don't do that on a blob basis, but Git does that. Git will restore contents in a directory based upon the tree in a commit. So when I switch branches, it's going to look at the tip of a branch. What's that commit? Okay, what's the tree in that commit? Let's take that and we're going to restore the files in the working directory based upon the state in that tree. So that's kind of the underlying workflow that Git goes through. Now we're skipping a lot of stuff, but that's the basic idea with Git objects, with hashing, commits, trees, blobs. There's also this fourth type, the annotated tag. We have talked about tags and annotated tags. Not a big deal. As this image loads here. They're not as important right now to understanding how all this works, but it's another type of Git object. They're hashed, they're stored in the objects directory. They include metadata, who made the tag, the date, a tag message, just like a commit, except that a tag is just a pointer to a particular commit. It is not an actual commit itself. So it kind of stores a reference to a commit, and a commit stores a reference to a tree, and a tree stores references to blobs. All right, I applaud you if you made it through all of this. I hope some of it made sense.